Hi, everyone. My name is Bryn Stewart, and I'm a postdoc here at Caltech. And today I'm going to discuss some of my work on connecting subsurface processes, stream water quality, and climate change, and how all of these things are related to non-point source pollution. So I study water quality at the catchment or watershed scale, where catchments or watersheds are just areas of land that drain all inputs of water to a common outlet, as shown in this figure on the right. And the reason that we study water quality at this scale is because catchments provide a boundary and a specific set of conditions for an ecosystem. So everything from the climate of an area to the vegetation on the land, the soils, geology, et cetera, all of those different characteristics influence the different reactions that occur within our catchment and sources of different solutes and how they kind of affect our stream water quality. And so water quality and non-point source pollution are driven by these landscape characteristics and catchment processes. And so as an example here, based on the topic that we're focused on today, we know that harmful algal blooms are largely caused by excess nutrient pollution. And so typically coming from nutrients like nitrogen and phosphorus, and those nutrients need to come from somewhere on the land. And so those nutrients have to travel from the land into our water and into our streams to cause these downstream effects. And so I mainly study the processes that control water quality kind of on the front end, where we think about how solutes are produced in terms of what chemical species are generated in a catchment and where they come from, and then how those species are then transported to our streams through different transport processes, and how they're carried through a catchment into our water bodies. And so just to kind of walk through how we think about this, very high level, starting with production, we know solutes can be produced in a catchment through biogeochemical reactions or added via human inputs, like we've talked about already. And some examples relevant to nitrogen pollution for biogeochemical reactions could be things like the decomposition of organic matter, nitrification, and plant uptake, whereas some human inputs that we think about are atmospheric deposition and the application of fertilizers and manure. And so the solutes that are in our catchment can then be transported to our streams through different hydrological flow paths, as I'm showing in this figure. And so some of the main flow paths that we typically think about include surface or overland flow over the land surface and into our streams. We can also have shallow soil water flow in the subsurface, where we have more of those soils. We have organic matter, plant roots, and things like that. And then lastly, we have this deeper groundwater flow path through the deeper part of the subsurface, where we have our rocks, we have weatherable minerals, and we eventually hit bedrock. And so as water flows through each of these different pathways, it interacts with some of those different materials that I just mentioned. So whether that's minerals or soils, organic matter, and those interactions shape the chemistry of that water as it enters our stream. And so as you can imagine, each flow path has this distinct chemical signature that it ultimately carries into the stream, and then they all mix together to form our stream water chemistry. And so this stream chemistry represents like an integrated signal of all those different flow paths and their chemical signatures, as well as all the processes that lead to the development of those chemical signatures. And so since we typically only have measurements of water quality in streams and rivers and not so often in the subsurface, we often have to infer where those solutes are coming from within a catchment. And so that brings me to one of the very broad questions in this field of research, which is what processes control solute production and transport at the catchment scale. And so one method or tool that I use in my own research to help address this question is reactive transport modeling. And so for anyone unfamiliar, reactive transport models are computational models that couple physical, chemical, and biological processes with mathematical equations. And so we can use them to simulate some of these important subsurface processes like biogeochemical reactions and hydrologic flow paths so that we can understand how they're influencing our stream water chemistry and those stream chemistry dynamics. And so during my PhD at Penn State, I helped to test and develop a reactive transport model called BioRT-HBV, which has a fairly simple structure and requires minimal input data, and is also computationally inexpensive, which is very helpful in a world where we don't always have the data that we need. And so as a quick overview, BioRT-HBV simulates the hydrology, biogeochemical reactions, and transport processes in a catchment. In this model, we get our hydrology based on the overall water balance between input precipitation, output evapotranspiration, and output discharge. And so just to kind of walk through this figure here, water can enter a catchment through precipitation. Some of that water is partitioned to evapotranspiration, or water evaporating from the land or being transpired by plants. And then the rest of that water infiltrates into our catchment subsurface and then can be routed to the stream through one of those different flow paths that I mentioned. So we have shallow flow, or surface flow, shallow flow through the shallow subsurface, and deeper groundwater flow through the deeper subsurface. And so we can implement some of those different biogeochemical reactions that I mentioned into the different subsurface zones that we have in the model, and that will influence the water chemistry that we have in each of our flow paths. And what's really interesting and helpful about this model is that the structure allows us to look at each individual reaction, each flow path, and each zone to see how each of those impact the kind of integrated signal that we see in stream chemistry, as well as all the different processes that lead to our stream chemistry dynamics. And so in my research, I've mainly focused on studying carbon. And so I've applied this model to the W9 catchment at Sleepers River in Vermont to simulate the production and export of different dissolved carbon species. But you could also use this model to study some of the nutrient species that we were talking about today, like nitrogen and phosphorus processes. And so I'm not going to focus or spend too much time on this example since we're not really focused on carbon today. But I just want to show a few slides here to demonstrate the capability of the model and what sort of insight we can gain from using a model like this. And so in this example, we were focused again on dissolved carbon species. And so the two main solutes that we were looking at were dissolved organic carbon, or DOC, and dissolved inorganic carbon, or DIC. And so those are produced by the different reactions that we've implemented in the subsurface zones there. And so basically when we run the model, we have our hydrology happening, we have these reactions occurring, and then the model calculates the concentrations of each of our solutes in each of our different flow paths and in the total stream chemistry. And so we get those concentrations produced from the model results. We also get flow rates for each of our flow paths and in the total stream discharge. And then we also have reaction rates on a daily time step. And so just to demonstrate, again, some of the insight that we can gain from these sort of model results, we can look at the total rates of net production and export for our two solutes here. So this figure shows 2 years of discharge and air temperature data up top, whereas the bottom two panels have 2 years of the model results, where we have production rates in gray and we have export rates in black. And so looking first at the production rates in gray, we can see that both DOC and DIC tend to have higher production rates under warmer conditions where we have our higher temperatures, typically in spring and summer in this catchment. But if we look at the export rates in black, we see that the dynamics here mainly match up with the discharge dynamics up top. And so this kind of highlights the different controls of climate through temperature on driving our solute production, whereas hydrology has a more dominant control on our export rates. And so the reason that we care about this is that these have implications for how climate change may affect our water quality moving forward. And so again, this study site was in Vermont in the Northeast US, where climate change projections include increased temperatures and increased frequency and intensity of storm events. And so with these model results, we can make some kind of broad inferences that higher temperatures in the future may lead to increased DOC and DIC production, whereas more frequent storm events may lead to more flushing events and higher discharge conditions that lead to more of these kind of higher export rates of DOC and DIC into our streams. And so overall, that would mean that we have higher concentrations of these dissolved carbon species in our catchment and in our streams, as well as higher fluxes of these dissolved carbon species from our catchment downstream. And so that example just demonstrates how we can use reactive transport models to make connections between observable data like stream chemistry, discharge, and temperature, and then the processes that we can't really easily measure or observe, like biogeochemical reactions and subsurface flow paths. But that kind of leads me to a limitation in this general field of research where our understanding of catchments and their processes is inherently tied to the data that we're able to collect and the climatic conditions that they represent. And so with climate change, those conditions are changing, and that challenges our understanding of these systems and how they function as we continue to observe more conditions that we've never really seen before. And so as an example, we know that climate extreme events are projected to increase in intensity and frequency moving forward, but so far they're relatively understudied in terms of how they affect our water quality. And so if any of you might remember that there were these historic storms and floods in Vermont last summer in 2023. Those storms led to 4 of the 5 highest stream flows that were ever recorded at my main study site at Sleepers River. One of them also flooded the capital city of Montpelier. And so these events are really important to study, and we don't generally have a lot of a clear understanding of how they work and how they are affecting our water quality. And so I'm currently working on applying our reactive transport model on an hourly time step to try to get a better understanding of these event scale dynamics and how they're influencing our solute production, export, and fluxes downstream during these storms. And so that brings me to some of the measurement needs and challenges for capturing and observing these climate extremes, where we really need high-frequency measurements that capture these event scale dynamics. And then we also need to integrate those data with reactive transport models to gain a better understanding of the processes that lead to those observations. However, one of the main challenges that we have in studying these types of climate extremes is how difficult and potentially dangerous it can be to go out into the field and take measurements during this time. However, we know that high-frequency sensors and automated sensors or samplers do exist, and they've worked in a good amount of places, but they also need to be robust enough to withstand any potential damage during these events. And I've heard plenty of examples where people lose sensors or other equipment during these types of storms. But this is, I think, a pretty achievable goal, and I would love to hear if anyone has successful experience in monitoring these types of climate extremes or protecting sensors under these conditions. And another quick example that I wanted to go through in terms of changing conditions due to climate change is the increase that we see in rain on snow events as we're having warming winters. And so here I just want to highlight some work from a collaborator of mine, Dr. Aaron Siebold at the Kansas Geological Survey, who showed that these rain on snow events pose an unquantified continental scale risk of high nutrient export during these wintertime conditions. And so in particular, she was looking at the Mississippi River Basin, which is shown in that black outline sort of in the center of the US, which drains about 40% of the contiguous United States, including a lot of agricultural land in the Midwest and the central US. And so these two maps just show on the left whether an area has high frequency of rain on snow events, and on the right if an area has high sources of nutrients like total nitrogen or total phosphorus. And so if we look kind of at the upper Mississippi River Basin there, we see that they have both high pools of nitrogen and phosphorus, of course, on the right, but also high vulnerability to these rain on snow events. And so this is a problem because these events can flush out those nutrients into our streams and contribute to the high nutrient concentrations that lead to hypoxia, eutrophication, and harmful algal blooms. And so these two plots just show mean turbidity versus mean discharge at 2 different sites along the Mississippi River Basin. And the dashed line in each plot shows how one particular rain on snow event that they were looking at in 2019 led to a disproportionate amount of sediment transport and likely also high nitrogen and phosphorus concentrations as well, as those species are typically co-transported in our streams and rivers. However, we currently lack sufficient data to fully characterize and monitor those different nutrient sources, their pathways, and their wintertime fluxes. And so these figures just highlight how stream nitrate data during that rain on snow event in 2019 that they were looking at was incomplete during that specific period, but also more generally during our wintertime conditions. And so the authors here were able to use turbidity data to get a general sense of nutrient export, but the exact response of nitrogen and phosphorus during this type of event was not able to be assessed. And so that leads me again to some other measurement needs and challenges in terms of studying these specific rain on snow events, but this also applies to other climate extreme events and studying kind of the difference between extreme conditions and non-extreme conditions, where we really need this kind of continuous year-round monitoring of hydrology, soil, and stream conditions at the watershed scale in order to assess the different processes that are happening and how that leads to changes in our stream water quality. And then another challenge here is that traditional sampling methods and sensors typically aren't designed for cold and icy conditions. And so that's typically why we often have gaps in our data for wintertime conditions, And that's really limited our understanding of different processes that happen during the winter, how those events might be influencing our water quality downstream, and how much they might be contributing to these issues like hypoxia, eutrophication, and algal blooms. And so I talked a lot faster than I really meant to, and I'm sorry about that. But to wrap up, we can see that climate extremes and climate change can have important effects on water quality, but we really need to combine, I think, field efforts and modeling efforts as well to study these events in more detail and to kind of get a better understanding of how much they're contributing to changes in stream water quality moving forward. So I'll leave it there, but thanks very much for your attention, and thanks again to the workshop organizers for putting this on.